Hello everybody. This is going to be my final project presentation. It's going to be on electrical theory. We're going to go through some of the fundamentals that we ran through this semester. This is definitely a presentation catered more towards electrical apprentices and stuff that we see on a daily basis as electricians, helping us become better troubleshooters in the field, working on things such as like VFDs. Instead of just being installers, we're going to want to be able to understand some of this theory so that we can apply it in the workplace and be better troubleshooters. For slide 2 here, we're going to go through the presentation agenda for my topic. So we're going to start with DC theory. We're going to go through Ohm's law, series parallel circuits, and then for solving any of those variables like voltage, current, and resistance within those circuits at any point, we can use Kirchhoff laws. We're going to move into DC theory. We're going to try and understand better sine waves, and instead of voltage, current, and resistance, we'll be looking at like things like impedance, reactance, and then looking at solving maybe some RLC circuits with inductors and capacitors, and why that changes things a little bit. We'll then be going into some solid state work. So in this semester, we definitely talked about diodes, transistors, SCRs in industry, which is things that we can see on a daily basis and are going to help us learn how to troubleshoot some of the more complicated systems. And then we'll look into even further digital circuits, such as like logic gates, or digital components like logic gates, binaries, VFD integration. So stuff that works in VFDs, but also these are the groundworks for like things like computers. So really cool stuff, guys. We're going to work into the next slide. So for the third slide here, we're going to be talking about why theory even matters. So in our industry, we have a couple things that are going to make a big difference here. So like safety and compliance. Theory explains why the NEC even exists, right? So why is electricity dangerous? Why is wire sizing important? And why would we even account for things like voltage drop? What does that matter? Troubleshooting. So as a wire puller guesses, a technician analyzes, right? So when you're looking at a VFD, do you even know what's going on, right? If you don't, how are you possibly going to try and fix it? These are important things to know, guys. So the theory lets you trace invisible faults. When you're having issues, whether it's in a residential setting, an industrial setting, whatever, you're going to want a course of action to start testing some of the reasons why these circuits aren't working, how you can fix them. And in modern systems, things like VFDs, PLCs, without understanding the logic behind these wirings, you're going to be in the dark. So this is the big difference between being just a wire puller and a technician, right? So you don't want to be just out there guessing. That's how mistakes are made and how we can get into dangerous situations. So DC theory foundation, this was like year 1 stuff, guys. So V equals IR is the most common relationship that electricians deal with on a daily basis, right? So voltage equals current times resistance. Voltage is going to be the electrical pressure. You can also think of it like a potential energy, right? It's electrical potential. It's the pressure that the electrons are feeling through the wire, right? Current is going to be, if you took a slice of that wire, how many electrons are going through per second, right? So it's a flow or a rate, and the unit is going to be amps. So resistance is the opposition to that current, right? So if you had a big raging river, the pressure would be the angle of the river, right? The gravitational angle pushing the water down. You could think of the flow as the water that's crossing your plane of sight per second, right? And then the resistance might be some rocks or anything in the river that's slowing that water down, maybe a curve, anything that's causing that water to slow down. This relationship governs like all the DC circuits that we're going to be dealing with. A lot of the calculations are pretty easy in DC, especially in the series circuits. When it gets into parallel, it gets a little more complicated, but we're going to run through some of those calculations real quick. To series circuits here, the one path rule. In a series circuit, you're not going to be splitting it up like we do in a residential setting or any of the industrial settings where we use parallel circuits, right? So here you can see there's a battery and there is one path for the current to flow. It goes through a fuse, and it goes through maybe a disconnect here or something. It goes through 2 resistors, then comes right back to the negative terminal of the battery, right? So the things you got to be worried about with series circuits, the current is constant throughout. So no matter whether I'm here before the fuse, after the disconnect, after the resistor 1, after the resistor 2, the current is going to be the same in every location in a series circuit. The resistance is additive, so every resistor I have in here, it's going to add throughout the process. So the total circuit is going to be the sum of all resistors within it. The voltage, it's going to be divided across the loads, right? So across the fuse, you got to think that what energy is being used there, right? So like there's going to be a voltage drop across the fuse, maybe if there's some heat being produced there, maybe across the disconnect if there's like, I don't know, bad connections and there's some heat, and especially across the resistors, you think like a light or any, maybe an outlet or something, which I guess that wouldn't really work in a series circuit, but that's going to be causing a voltage drop. And you're going to notice that the voltage total is going to be a sum of all the voltages used up, or the voltage drop across all these resistors or components within the circuit. We go through series circuits, we can move into the parallel circuits, which is more what we use in our industry. So we're going to be looking at some of the multiple path rules, right? So the most electrical loads like lights, outlets, everything in our industry are mostly wired in parallel. The voltage is going to be constant across all branches, right? So if, at any point in the circuit, if you measure in an outlet, those are all wired in parallel. If you measure anywhere in the circuit, you're going to get 120 volts typically, right? So the voltage total is going to be equal to the voltage 1 plus voltage, or which is equal to voltage 2. It's going to be the same everywhere. The current is going to be additive, right? So this goes into like what we'll learn in the Kirchhoff laws, which is like the node rule, right? So like if current enters in one spot and then it branches off into two locations, that current that enters is going to be equal to the additive, or the current 1 and 2 is going to be equal to the total current, right? So where it branches off at a node. The resistance is going to decrease as you add loads. So the more loads, the lower the total resistance the circuit feels, right? So it's going to be the inverse of each resistor or each load. We're going to go into the Kirchhoff's voltage laws, right? This voltage law is going to be called the loop rule. So the algebraic sum of all voltages in a closed loop must be equal to 0. For the example here, we're going to have a 24 volts source feed, 2 resistors in series, 4 and an 8 ohm. So this is pretty simple, right? So we're going to be looking at the loop here, and the sum of all of these voltages should be equal to 0. So across the battery, we're going to have a positive 24 volts, and then across each resistor, we're going to have a negative. In order to find the voltage drop across each resistor, we're going to want to calculate the current within the system. So we have to add up the resistors. 4 plus 8, we're going to have a total resistance of 12. And then just using V equals IR, we can do 24 divided by 12 ohms, which is going to give us 2 amps. And then you're going to look at that 2 amps times the 4 ohms using the voltage equals current times resistance equation. And that's going to give you 8 volts across this resistor. So I start at 24, I'm at 16, so I'm going to be looking for a 16 volt drop across this resistor, which I get 2 amps times 8 is going to give me 16. So I would have 0 volts here on the negative terminal and 24 volts on the positive terminal, right? So that in the loop, it's going to be a total drop down to 0. The sum is positive 24 minus 16, or minus 8, and then minus 16. That gives me a total sum of 0. Next rule that Kirchhoff made, which was the node rule. In this rule, it basically says that the total current entering into a junction is going to be equal to the sum of the current leaving. So if we have a node that has 10 amps entering from the source and it splits into 2 branches, we have in is 10 amps. Let's just say that branch 1 draws 4 amps. That just means that the second branch is going to have 6 amps, right? It's going to be the sum of them both, right? So what is the current in branch 2? It's going to be equal to 6 amps. 10 amps equals 4 amps plus whatever the remainder is. So I know a little bit more complicated of a scenario here. I'm not going to do all the math for you here because it gets a little bit hazy, but if you look up any YouTube videos on how to solve these equations, it's not too bad. I personally like to find where the current or the total current is in the system using the node rule. So you'd have your current 1, which would be the same here because it's in a series, and then it would divide into current 2 and current 3, and then out of this junction it would be current 2, current 3, and then it would go back into current 4, or well, it would be current 1. These two would be equal. but then you can use that alongside the voltage drops and all that stuff to calculate these. Just for this example, we have a 24 volt source feed and we have 3 resistors. R1 is in series with R2 and R2 and R3 are in parallel to one another, and you can break this down into a series circuit by just simplifying these. The parallel equivalent would be 1/6 of this resistor, remember, because it's inverse, 1/12, and then you inverse that and you get 4 ohms. And then you're going to find that the total resistance, now that this is equivalent to 4, is 2 plus 4, which is 6. Then you can find the current, which is going to be 4 amps, using 24 divided by that 6 that you found for resistance. So then you have the amperage here, and then the amperage is going to divide up here, but you can simplify it down to find that the drop, the loop rules are going to show you that the drop in loop 1 is going to be equal to 0, and the drop across loop 2 will also be equal to 0, right? Yeah, so check loop 1, 24 minus 8 volts minus 16 volts, right? You're finding that 8 volts because 2 times the amperage of 4 is going to be 8, and then your 6 and 12 equivalent, if you basically just break this down into one resistor, it would be equivalent to 4 ohms. So then you do your 4 amps times 4 ohms, which gives you 16. So the voltage drop across these two would be 16, which would be 0. If you go the other way, you could think of this as a positive, so 6 times 4 amps. Well, the amperage would be different here, right, because of the node rule. So it would be 4 amps here, and then on this side and this side, it would distribute differently based on the resistance. So you can solve it multiple ways, but the idea here is that the loop rule works in the parallel circuits as well. Theory a little bit here. We were just talking mostly about DC. When you go into AC, you start learning about the sine wave. Unlike DC, AC polarity reverses 60 times per second, right? So you're going to be getting your highs and lows about 60 times per second. Frequency is cycles per second, and in most industry, it's going to be 60 hertz. Period is going to be the opposite of that, or the inverse, right? So time for one cycle. So how many seconds does it take for one cycle to occur? The RMS value is the effective voltage. This becomes important in our industry, right? Because the power output for a certain voltage in DC is not the same as it is in AC, right? So the effective voltage, VRMS, equals the peak times 0.707. Note, multimeters read RMS, not peak. So it's all designed in our meters. Inductive reactance, capacitive reactance as well. These two concepts, the inductive reactance is mostly going to be important in motors and coils. This opposes changes in current. This opposition is called reactance, right? So the inductive circuit's current lags voltage, which is important. So in our calculations, we're going to have a couple formulas here that we can use for inductive reactance. 2 pi times the frequency times L, which is inductance in henries, right? And then we're going to go into capacitive reactance, which is X sub C. Capacitors oppose changes in voltage. They are used to correct poor power factor, right? We all of us had Murbach, right? And he had a lot of examples of how he helped out a lot of industrial buildings by adding capacitors into their power banks to get better power instead of wasting a lot of it due to all the motors and stuff in the building. Capacitors oppose changes in voltage. They are used to correct power factor. In capacitive circuits, currents lead voltage. So if the inductors lag voltage, this leads, it's gonna make it corrected so that the power is being used properly. Capacitance is in farads, and the equation is going to be 1 over 2 pi times the frequency times capacitance, right? So we can use these to calculate some RLC or impedance equations, right? So in this series circuit, I have a resistor, which is 3 ohms, and an inductor, which is 4 ohms. We can't just add them like we do with resistors. It's not just 3 plus 4 equals 7. They're going to be out of phase slightly, right? So we're going to have to use the formulas. The formula is Z equals the square root of R squared plus X sub L squared. For this particular equation, there's another component for capacitance. You can Google it, look it up. I don't have an example for the slides, but you're going to substitute in your values. So a 3 ohm resistor, and then for the capacitive the inductive reactance, or the impedance. I'm sorry, the impedance is what we're looking for. I'm looking at the inductive reactance. Is going to be 4, so that is going to equal out to the square root of 25. I'm going to get 5 ohms of resistance in this circuit. The reason that this is important is because of the power triangle, right? So we have the apparent power, the reactive power, and the true power. So true power works as the work actually done, so for heat and lights and motors and all that stuff, right? Reactive power is the wasted power stored in the fields, right? So you don't want a lot of reactive power. The apparent power is the total power supplied. So you want the reactive power to be low, your true power to be more in line with the apparent power. Right? So you want to cut down on this leg of it, which you can do with capacitors. Like if you have a lot of inductors, it's going to cause this to widen. And then if you add capacitors, you can close that up and get cleaner power, pay for what you're getting, right? Instead of just paying for useless energy. The next portion of the slides are going to be based on the solid state diodes and rectification. The PN junction, a diode acts as a one-way valve for electricity. We spent the last couple weeks talking about this stuff. It allows current to flow from the anode to the cathode, but blocks it in reverse, right? So we have these two different materials. One is doped differently than the other and has holes. It allows current to flow through it, but not backwards, which is really useful for rectification. Diodes are essential for converting AC to DC in a straight line. The first step is powering electronics, right? So we have our AC sine wave coming through this rectifier, and it comes out half the waves it originally had, and it also doubles the frequency, giving you a smoother DC. So then we can talk about solid state transistors. So the electronic switch transistors, BGT or JT, MOSFET, these are used as a small signal to control a large current flow. You can use amplification. They also boost weak signals like radio waves into strong ones, and inversion. In VFDs, an IGBT transistors switch DC back into AC. This is going to switch DC back into AC thousands of times per second. Solid state SCRs and thyristors. So we're going to be looking at, they call it the industrial muscle, right? So the silicon controlled rectifier SCRs are heavy duty switches. These are used for things like gate trigger. They will stay off until a pulse hits the gate here. Latching, once on, they'll stay on until the current stops. That can be useful in some scenarios. And then you can think of this as used for some soft starters, DC motor drives, and welding controls. We can get into digital logic gates here too. So once you start looking into logic gates, I personally think of this stuff as like more like computer uses, right? So like zeros and ones, right? Automatic or automation logic is built on simple decisions. You have AND gates, you have OR gates, you have NOT gates. All inputs must be true, right? So for an AND gate, you have to have A and B receiving a signal for Y to output a signal. You have to have, for an OR gate, either A or B seeing to release a signal on the Y end. A NOT gate is if you are seeing a signal, the Y will put out a signal, but if you're not seeing a signal on A, then you're not going to get a signal out, right? Pretty simple stuff, but they're very, very useful if you look into the binary system, right? So zeros and ones, humans count on a base 10 scale, computers see it in a 0 and 1 scale. Why it matters is every PLC, programmable logic controller, it has inputs in a single bit, or 0 volts or 24 volts. So it sees your voltage or it doesn't, right? So zeros and ones here. Grouping 16 inputs creates a word. So binary 101, you have 4 signals of 1, and then you have 2 signals at 0. Then you have another signal at 1. This is 5, which is a decimal, right, in computer language. Pretty cool stuff. Integration inside of a VFD. So variable frequency drives use a lot of this stuff. You can say that we have an AC input, three-phase sine wave enters. You have a rectifier, a solid state rectifier, which diodes convert AC to DC here. So entering into this DC link, it's going to smooth it out or filter it. You have DC bus, DC theory capacitors smooth the voltage. And then you're going to have an inverter which brings it back into DC to put it out to a motor or something. And a lot of the controls are done off that DC. So you're going to want voltage in, turns into DC, controls all the outputs, and when to start, when to stop, and the logic, right? So that's all important stuff in our industry. Conclusion: a mastery of theory transforms you from a part changer into a true diagnostic expert. And by no means am I saying that I am an expert on any of this stuff, but I do think it's very important that we study this stuff in school and even after school start looking into some of this stuff. Very interesting information to know and useful on the job site. Here's some of my sources, and that is my presentation. Sorry if it was a bit long.